Hello everyone, this is Noah again with problem sets 6 and 7. So we're going to start with 6 first. These problem sets are super simple if you just kind of get what their equations are and then what their equations are saying. So for example, in problem set 6, we have this equation where energy is equal to negative z squared, where this z is the atomic number of an atom, times a constant, times the Planck's constant, times the speed of light, over n squared, and n is the energy level that the electron is in. So this is just how you tell the energy of an electron, in the energy level. This equation also tells you the energy, but this tells you, forgot parentheses, this tells you the energy when an electron changes energy levels. And so you have the constant again. This might be Rutherford's constant. I don't know. And Planck's constant, the speed of light, times 1 over the first n squared minus 1 over the second n squared. And so what this says is this tells you how much energy comes from either an absorption or an emission. In question 1 of this problem set, it asked for it told you that these three constants over 1 squared is equal to that. So that's just over 1. So that means that these three constants equals that. And it comes out as a negative in the question, but these are all positive constants, so it comes out positive. But negatives for some reason are weird in this, so we just have to kind of accept it. Just switch the signs if it's weird. Just kind of accept it because that's what they've been doing on the problem set. And where are the right answers? So since these three constants are right here, I'm just going to plug in this number right here. And so 2.18 times 10 to the negative 18th is, I guess we can just treat as a constant that we're going to use for this energy changing. And then this equation, the rest of the equation still holds. So why you have to deal with switching the signs is because if you have a number drop from a higher energy level to a lower energy level, for example, 5 to 1, this number comes out negative. Why? Because you have 1 and then it's squared, so it's 1 over 25 minus 1 over 1, which is just 1. So you have 1/25 minus 1. That's going to be negative. No matter in any situation, if you have a number bigger than 1, then you're going to be dealing with a negative. So any emission of energy is going to come out as a negative. So in the problem set, I looked, and it's true. They just switched their signs. If they came out with a negative answer, they just switched their signs. So I think it's safe to say that you can treat this as a negative number if it makes you feel better, or a positive number. Just know when it's an emission, it'll be negative. When it's an absorption, you can treat it as positive. It'll be okay. So now the question is, what does this equation mean? What does this show? This shows that the energy levels are at first large values from one another, but they get smaller and smaller as they go up in n value. So I've drawn n1 far to n2, far, but then as it gets closer and closer until it's just basically a block at n equals infinity. This is shown in this equation, and it's shown here of why that's true. It's like you're taking a limit. As n2 goes to infinity, then it just becomes n1 kind of thing. Okay, so what does an absorption? So part of the problems, we're taking this diagram here, and it said, what does an absorption look like? Well, an absorption is when an electron gains in an energy level, and so it's going to look like this. This absorption is going to be more energy. Say it's going from N2 to N3, 4, 5 up here. That's going to be more energy than if an arrow from here went up to N equals 6. Why? Because these are spreading far apart. And it's probably good, if we really don't know, if we're really unsure about which one has more energy that's being absorbed, it's probably good to just plug these into the equation with their n values. And if that's not possible, just know that it's a bigger jump from these lower values than it is from these higher values. So you might want to think of like, how far of a jump is it? You know, if this was a river with rocks and the first rocks are far apart from each other, you think, okay, which one's the harder jump? Is it from 1 to 3, or is it from 3 to 6? And you just look at that. When it's an emission, that means an electron is dropping the energy level because it's releasing the energy, and we see that energy, and that's why it's called an emission, and that's why things will glow. So an electron going down will be like this, and then same thing with the energies from absorption. So this one will be maybe less energy than this emission. And then the size of the arrow of how many energy levels is taken into account as well. So now how do we tell the energy from the diagram? We've talked about that with the arrows. Now how does this relate to light? So the energy, we know from this equation, is equal to the lambda times the frequency times nu. And so we have the energy, and we want to know the lambda and the frequency. So we can use the other equation. This equation isn't true. It's C equals wavelength. There we go. Okay. So from this, and then E equals HV, we can plug into there. And then from these two equations, we can find that from the energy, we can get this wavelength. And from the wavelength, we can tell if it's visible light, if it's not visible light, if it's harmful radiation, or if we need, if it's a radio wave, things like that. So this tells us if we can see it or not. So there's some energy level changes that we can't see. Very good. Okay. And again, just solidify, energy is equal to this number, 2.18 times 10 to the negative 18th, times the Z. If you're dealing with hydrogen, that's just 1 squared. And then it's 1 over first n squared minus 1 over second n squared. Very good. Okay, let's go to problem set 7. Okay, so the equations in this one, like I said in the beginning, that these problem sets are just about understanding the equations. So the equations at the beginning is lambda is equal to h over mv. So what's that saying? That's saying that matter moves in waves. How he did that, I'm pretty sure he just combined, and if you can get a doctorate from this, that's amazing. He just combined the equations we already know and came up with this. Incredible. In my mind, I think that's incredible. So there's another equation. Now that they discovered that light, that energy, all matter moves in waves, now they want to know, well, how does electrons move? And so we came up with this uncertainty principle, that because you can't tell where a wave is, you know, if I said, where is this wave? You'd be like, well, it's here. I mean, but it's also here. And it's also here, I guess. You know, you can't tell where it is. Like, well, you can, but like specifically, you can't say a point that it's at. So this uncertainty principle is given, where it's the change of x, and this is on our equation sheet. The change in x is equal to the change of mass times velocity, is greater than or equal to Planck's constant over 4 pi. Don't forget the 4 pi. I always kept forgetting the 4 pi. So you want to multiply if you have an uncertainty either value or percentage, then you want to multiply that by the velocity. Usually if they give you a value, it'll be in meters per second. And then make sure you convert to meters per second as well. This equation only works for meters per second and kilograms. And so multiply the uncertainty percentage to the velocity. We got that? Okay. Wave functions, so this is the very complicated equation that Schrodinger came up with this trident-looking thing called psi. What this function gives you is solutions to, or the solution is, it defines the allowed energy. So that I will come back to that in just a second. Then quantum numbers combination describes one of those solutions to this Schrodinger's equation. So the quantum numbers is what we get with the orbitals. It's the combination of the three, and it tells us, really, it's a better way of describing where this, you know, the electron is, the probability of it, and in that energy level that it specifically is at. Psi squared gives us the probability of an electron in a certain energy existing. So I think this is interesting because when we describe orbitals, we have n as the energy level, and when we take n squared, it equals the number of orbitals. I don't know if those two are related, but I think it's interesting and will help me remember that this tells us it defines the energy, the allowed energy, and the energy level squared, just like this squared. This gives us the probability of an electron in a certain existing area, and this gives us the number of orbitals. So I thought that was related. And then the quantum numbers that we have is we have n, and then L is n minus 1, all the values from equal to 0 above to n minus 1. So I've drawn in brackets 0 to n minus 1 is all those values. In integers, write that. And then m sub L is just equal to negative L to L, also integers. So those are the relationships between the two. And then one combination of the three. So if I have 2, 1, 1 in these three combination numbers, this equals one orbital. And so when you're looking for how many orbitals, you do take this and just square it, but you also want to count out it's all the combinations of these orbitals. So I have, if this was 4, then I have 4 possible here, and that means I have 9 possible here possibilities. There's also in that, if L equals 4, there's also possible subshells in that as well. Okay, those are problem sets 6 and 7. Thanks for watching.